Good afternoon and welcome again to the SETI Institute. This is again our weekly colloquium series, which we bring to you every Tuesday at noon, and we're delighted to see new friends and old friends and familiar faces at our weekly talk series. And we're continuing today on the theme of exoplanets, where we had a nice talk last week from one of our own researchers. And as I said last week, I confessed to having a bit of favoritism toward the exoplanet work and the work of Kepler, but also GPI, because I find the results in terms of the number of planetary systems that we're discovering and the number of exoplanets we're discovering to be rather profound in the extreme. So we continue the theme today, and I'm delighted to be introducing to you Dr. Bruce McIntosh from Stanford University. He will be speaking to us. His presentation is called The Direct Imaging of Extrasolar Planets and the Gemini Planet Imager, of which he and his colleagues are pioneers in new instrumentation that is allowing this imaging capability. I will tell you that with my good friend and one of our trustees, Pierre, we saw Bruce speak on this topic back in May at SLAC, and it was astounding because I think that at that talk, one of the first public displays of direct imaged exoplanets was shown to a wide audience, and it was pretty mind-boggling, very impressive to see. So a little bit of background on Bruce. Bruce is a professor of physics at the Kevley Institute for Particle Astrophysics and Cosmology at Stanford. He obtained his PhD at UCLA, working on infrared instrumentation and searches for low-mass companions to stars. As a postdoctoral researcher and staff scientist at the Lawrence Livermore Laboratory, he worked on using adaptive optics to sharpen images made by ground-based telescopes at the Lick and Keck observatories. He co-led the team that made the first ever images of an extrasolar planetary system, discovering 4 giant planets orbiting the young star HR 8799. He's a principal investigator for the Gemini Planet Imager. And for those of you who saw the announcement a few weeks ago, the press release from Stanford, and also we put this on our own website, he was the principal investigator and lead author on a paper about 51 Eri b, which is a Jupiter-like gas giant, also directly imaged using the GPI system, and it's orbiting a star about 100 light years from here. So pretty amazing and interesting stuff. And without further ado, I'd like to ask Bruce to come up and tell us about his work and the Gemini Planetary Imager. Thank you.
All right. Thank you for the introduction and also the opportunity to come here and speak at SETI. As I said, I'll be talking about direct image of extrasolar planets and the Gemini Planet Imager, GPI, which is an instrument deployed on a telescope in Chile. Not this telescope, actually the next telescope over, but the view looking in this direction is better with the condor in the foreground. And this represents the work of a very large collaboration of people, and I'm obviously could fill up the whole hour reading the names and highlighting the roles of the individuals, which I won't do. But in particular, James Graham from UC Berkeley, who I think actually did an earlier talk on this, except at the time he wasn't allowed to talk about our newest results, so I get to cover more. And also SETI participants, especially Frank Marchese, who I've been working with in one form or another for more than 15 years, originally on planets in our solar system until we got kind of bored of those and moved on to the extrasolar planets, who's a PI here at SETI, Eric Nielsen, who's a postdoctoral researcher who works for Frank and myself, sort of splitting his time between SETI and Stanford, and Sarah Blount, who is a summer student here who did some really excellent modeling of the system that I'll be discovering. So you've heard a lot of exoplanet talks. You don't need to be told why it's interesting to do. It's one of the most interesting questions, in my admittedly biased opinion, in not just astrophysics but science, and it's a question that's people have been thinking about for 1,000 years or more. Are there many worlds, or is there but one world? It's a question we now know part of the answer to. We know there are a lot of other planets out there. We know, depending on how you count, 1,000 or 2,000 extrasolar planets orbiting other systems. So our level of knowledge has expanded enormously in the past 20 years. But our level of ignorance, as is often the case in science, has also expanded enormously, in that of these thousands of planets, we really have no clear understanding of the process that formed them, of the nature and the composition of whether solar systems like our own are somewhat rare, incredibly rare, or uniquely rare, and many other questions. And a large number of researchers with a large number of techniques are working together to answer that question. Missions like Kepler have been absolutely crucial in it. But the direct imaging that we do is also important now and going to be even more important going into the future, and that's what I'll talk about. Again, with history, we'll just go back a long way. This is before I went to graduate school, the view of the universe, which basically consisted of the Earth as being the center of the universe and a bunch of stuff that wasn't the Earth going around and around it. And you can kind of see why that's a natural model for the universe. If you're standing and you're patient enough to stand all night, you watch stars rise, you watch stars set, you get the feeling that it's all moving relative to you. Plus, it's a natural assumption if you're human beings to assume that you are the most important thing there is. The problem with that, of course, is that that model did a terrible job of predicting the way planets would move. This is an animation put together by someone at OSU in a Ptolemaic view where the Earth is at the center of the universe of the ways the planets have to actually move to reproduce what we see. So the sun, the Earth is sitting there in the center. All the other planets are going around it as I start the animation. And you can see, oh yeah, the sun goes around, that's nice and easy. But to reproduce what we actually see, Mars, for example, has to make these giant, great swoops, because if you watch the position of Mars night by night, sometimes it moves forward, sometimes it moves backwards. Very hard to understand if all it's doing is going around the Earth in a relatively simple way. So if the Earth was the center of the universe, you have to have this incredibly complicated pattern of things referred to as epicycles. On the other hand, if you put the sun where it's supposed to be in the center of the universe, like the animation now shows, it's a fairly natural behavior that sitting on the Earth, watching the other planets go, sometimes you're overtaking Mars, and so Mars will appear to be moving backwards relative to you. Other times, you are moving on the opposite side of Mars, and it'll appear to be going forward relative to you. So if you put the sun in the center, as we all know, the universe gets pretty straightforward. And the first people to really do that definitively, Copernicus and Kepler, produced quantitative models that use this idea of a heliocentric universe to explain the motions of the planets. So Kepler, also together with Tycho, took positions of the planets night by night by night. Kepler took his model in which they moved in elliptical orbits around the sun and could use those to predict a week, a month, a year more in advance where the planets like Mars would be. And for a scientist, that was really the conclusive proof of the fact that this heliocentric model was correct. So that's sort of the theoretician's approach to understanding the universe. The direct imager's approach is more like this. Galileo, the first person to really take an astronomical telescope. It's a really bad sign when scientists compare themselves to Galileo, by the way, so please forgive me for this. But he actually took a telescope, he looked at it, and he saw one of his first nights Jupiter and 4 little dots around it. And then he looked at it the next night, and the next night, and the next night, and he saw that these 4 little dots were moving, that night by night Jupiter was surrounded by things that were at different positions. And he very rapidly realized that means that things were orbiting around Jupiter, that not everything had to orbit the Earth, but there were independent individual objects orbiting around something else, in this case the moons of Jupiter going around Jupiter. And it's interesting in some ways that that visual proof, actually seeing other objects, moons in this case, orbiting other things, a planet, just like seeing other planets orbiting other stars, was sufficiently visually compelling that Kepler, who actually did the math to prove the heliocentric model correct, didn't actually get into trouble for it. The guy who actually looked through the telescope and said, look, little dots, really, they're not going around the Earth. That was something that the church could understand and got upset about and locked him away for. So there is something specifically exciting about seeing objects, whether they're moons or planets, that isn't necessarily quite as exciting as plotting the positions of objects on graphs night by night. And of course, back when they were doing this, there were 6 planets in the solar system. Briefly, there were 9. Now we're down to about 8, depending on how you count. And with a clear distinction in our solar system between rocky planets, nice small things you can walk on close to the sun, and giant planets, big puffy gas balls far away from the sun, with the dwarf guys kind of in the middle to mess it up. And of course, a clear relationship that Kepler demonstrated between how long they take to orbit and where they're located in the solar system. And so when I went to graduate school, mostly nobody talked about planets because planets weren't very exciting for astronomers when I was in graduate school. To the extent that they did, we were taught a model of forming solar systems that did a really good job of making our solar system, because that's, embarrassingly, a pre-Copernican way, what we thought the rest of the universe would look like. And that model starts with a star surrounded by a disk of gas and dust, as in this animation, and that disk of gas and dust gradually forms the nice flat set of planets that we see. In a more cartoony fashion, the large disk of cloud of gas that's going to form the sun collapses down. As it collapses down, it starts to spin faster, just from conservation of angular momentum, and hence flattens out. Ultimately, you have a sun. I'll try to be fair about pointing in both directions. You have a sun surrounded by this flat disk. because the little proto-sun is hot, the inner parts of the disk are hot, the outer parts of the disk are cold. And in turn, that makes a difference to the composition of the disk. Close to the proto-sun, the only way for something to be solid, for something to be a rock or dust or a planet for that matter, is if it's made out of something that's solid at high temperatures, like rock or iron. Far away from the sun, where it's cold, ice, water can be solid, hydrogen and oxygen, carbon and oxygen, very, very common materials. And so as a result, early in this formation process, it was thought there'd be a lot more solid material in close, a lot more solid material farther out, a lot less solid material in close. In turn, that makes it easy to make big planets far out, where you've got lots of stuff to build up a core at the center of a planet, rapidly enough that it can then absorb the gaseous material from the disk around it. Close into the sun, where solid materials are rare, it takes a long time to form something the size of the Earth. By the time the Earth formed, all the hydrogen gas was gone, so the Earth didn't get a big hydrogen envelope. So this model said you form planets gradually, you build their centers first out of solid material, and then you suck in the gas from the disk, and in turn, you can only really do that efficiently close, far away from the star. And of course, this model, like all scientific models, had to survive being tested by observations. It just took a long time to do that. The first observations to see planets, as you all know about if you've been to a bunch of planet detection talks, were done through Doppler shifts, where it's noticing that as a planet orbits around a star, the star wobbles, and it produces a tiny Doppler shift, a tiny change in its spectrum towards or away from the Earth, which can be measured by precision telescopes. That resulted in the discovery of a large number of massive planets like Jupiter. The other dominant way of finding planets, again, you've been to lots of these talks you're familiar with, are through transits. If through an astonishing coincidence a planet lines up so that it's exactly between the star and the Earth, as it passes across the disk of the star, its shadow will cause the star to get just a little tiny bit dimmer as observed from the Earth, shadow that the star and the planet cast onto the Earth. That tiny bit dimmer is about 1% for a planet the size of Jupiter, which is actually pretty easy to measure with modern digital cameras. And in fact, you can see this effect even with a tiny telescope. There are people who do this with networks of telescopes that are literally this big. Someone actually detected a planet using this method from a telescope in his backyard in Pleasanton, I believe, and published a paper on it in collaboration with real astronomers. And with modern digital cameras on your home telescope, you can successfully do this. Of course, the odds of it happening for any given star are astonishingly small because it has to line up just right. So if you want to find a lot of these planets, you need to look at a lot of stars. If you want to see a small planet, you need to look very precisely because the signal gets smaller the smaller the planet is. And by far the dominant thing, as everybody in this room knows, for doing this is NASA's Kepler mission. It looks at 100,000 stars by staring at a huge area of the sky and can see fluctuations in the star-planet brightness at the level of a few parts per million, small enough to see planets like the Earth. I was told I'm allowed to show some graphs in this talk, so I'm going to show a graph, given that we have people with assorted technical backgrounds. This is a common way for astronomers to think about the populations of extrasolar planets. It's a plot of planet mass versus semi-major axis, where every dot represents a planet that's been discovered by different techniques. And in this diagram, you can see the planets that are discovered by the Doppler shift technique, which is good at fairly big planets, down to a few fairly small planets, and very good at planets close to their star. You can see the planets that are detected through the transit techniques, especially Kepler, with some color coding for planets that have been seen through both techniques, and a spattering of planets through other techniques, including my direct image planets, which I'll get back to in a little bit. I've highlighted roughly where our solar system goes. And one of the striking things about this, of course, is it looks nothing like our solar system. Our solar system had this segregation, rocky guys here, giant ones here. Instead, huge numbers of giant planets have been found close to their star, and large numbers of planets have been found whose size is just in between the smallest of the giant planets and the biggest of the rocky planets in our solar system. And here's another version of that, just a graph showing from Kepler planet candidates as of January 2015 versus size, the number of planets. A few Jupiter planets or bigger than Jupiter planets are fairly common. But one thing Kepler has shown is this huge population of planets whose size is somewhere between Neptune's and the Earth's. From Kepler, that turns out to be maybe the most common kind of planet in the universe. There's nothing like it in our solar system. In addition, there's just no easy way to make these giant planets form close to the sun because we think there shouldn't be enough material for them to do it. There's no obvious way to make quite so many planets as Kepler sees down here. And so planet formation as a theory is really, there aren't any planet formation theorists here today, are there? Good. Is really trying, Jack Lissauer would beat me up if I said this, but let's say it's still trying to recover from the observations, and there's no single model that can predict all the planets that we successfully see. But broadly speaking, you can divide the models that still exist into two categories. The first category are still based on the core accretion picture I showed before, where you form the center of the planet first. I'll show some slides of that, and the outer parts later, maybe followed by migrating it. As the planet forms in the middle of this disk, it'll experience a thing like friction with the disk. It's a gravitational friction, but it's like friction that slows the planet down and causes it to spiral into the star. And so that's a good way to get giant planets close to the star. It's actually surprisingly natural that this should happen, and surprisingly hard to stop it happening in computer simulations that make it. So one of the questions is, why didn't it happen in our solar system? Why don't all the planets get eaten by their stars, et cetera? That's a slow, where slow means millions of years kind of process. When it forms planets, it forms them from the inside out. So it forms a core of a planet and then sucks up the outer material. The composition of the planet, I'll show in a couple of slides, will vary a lot. It also uses up a lot of the energy of the planet, and that'll be important when I get to direct imaging planets. And so it's sometimes referred to as a cold process because the planet ends up relatively cold. There's a lot of variations on this. It's very trendy these days to have kind of swirling clouds of pebbles that form the planets to concentrate the mass and make them accrete more rapidly. And finally, we are pretty sure this is a good process for forming rocky planets. A variation on this is still the best explanation for our solar system. We know that formed rocky planets because we're standing on one, and in simulations it can do a good job of forming rocky planets in other solar systems. Just to show a cartoon of that and allude to how it affects the composition, here's a cartoon of a star and a disk of material around it. And in numbers, I've written down the ratio of carbon atoms to oxygen atoms in that disk. And that'll be an important number that we'll get back to later on. In random clouds of gas in the galaxy, in our sun, that ratio is about 0.555 or so. If this model where solid material freezes out is true, that ratio can actually change a little bit. There's a place maybe 10 astronomical units away from the star for this particular star that I've done my cartoon about, where water forms into solids. And so out in the disk from there on, they're little lump grains of solid water ice. Far enough out, carbon dioxide can also freeze, and so there's lumps of frozen carbon dioxide. And in turn, that'll change the ratio of materials in the gas. If water ice forms, that sucks up a lot of the oxygen, and so there's not as much oxygen left. And so the ratio of carbon to oxygen in the gas of the disk goes up, where all the oxygen got sucked into solids. Farther out, the carbon gets sucked into solids too, but even more oxygen gets sucked into solids, and so the ratio goes up. Close in, where none of these ices are, the ratio stays kind of the same as it was when the disk formed in the first place. In turn, if I build a planet out of those materials, by say taking those little lumps of ice, making the core of the planet, and then sucking up a lot of gas around it, and maybe dumping some more lumps of ice in it, I can get an envelope for this planet whose carbon to oxygen ratio honestly can be almost anything, but can be different than the disk was in the first place. So because you form a planet a piece at a time, the exact order in which you mix in the solids and the gases can cause the planet to have a chemistry, a ratio of materials like carbon and oxygen and hydrogen that's very different than the gas that you started with to form it. And we see that very clearly in Jupiter. Jupiter is clearly enhanced in heavy materials because a lot of what went into Jupiter were these ices that caused it to form in the first place. The other way you could potentially form a lot of exotic planetary systems is a fast process, referred to as global instability, but I just like to call it collapse, where the big disk of material, as it orbits, starts to form little instabilities, little spiral structures in this simulation. Those in turn, under the influence of their own gravity, can compress even further, concentrate down into little lumps, and there's some lumps forming, that would ultimately become planets. This process, if it happens really fast, and in fact it's a problem with computer simulations that it happens way too fast to be plausible right now, but it would probably happen still fast, not millions of years, but tens or hundreds of thousands of years. And when it happens, you just basically scoop up a whole big lump of the disk and squish it down to be a planet. And so the composition of the planet is the same as the composition you started with for the disk. So you end up with planets that look like the original cloud of gas that they formed out of in the galaxy. No extra carbon, no extra oxygen or anything like that. Because it happens so fast, the planets don't have a chance to lose any of their energy, and so they form really hot. And again, that'll be important as we'll get back to it later on. And because it really just scoops up a bunch of disk material, it's a really terrible way to make small rocky planets. Most astronomers would say this is not the predominant method of planet formation, which is good news, because if it was, then rocky planets would be relatively rare. So as people went on to study these planets, we got very excited by the first results. We have beautiful press release figures. This was sort of one of the earliest Doppler planet detections. You can even see the artist has added a little moon getting evaporated by it. You think it's a planet just like Jupiter. But of course, when you see a planet through a technique like Doppler shifts, you don't know that. All you know is that there's a planet that's going around the sun. You know what its mass is. Absolutely nothing else. Kepler measures in a different way. Here's another artist conception example of really nice Kepler press releases recently about planets that are analogous to the Earth, orbiting in the so-called habitable zone or Goldilocks zone of their stars. This is, I think, the one from a year ago when Kepler found a planet just like the Earth, as opposed to the one from this summer where Kepler found a planet most recently just like the Earth, or the one 2 years ago, or the one 3 years ago. There's a series of Kepler results along these lines. It's very exciting to think about the possibility they could be planets like Earth, but again, well, the artist's conception shows little continents and maybe tiny seas or oceans on it. All we really know is the radius of the planet and nothing else. The planets Kepler are finding could be rocky ones we could walk around on, super Earths. They could be micro-Neptunes with giant hydrogen gas envelopes, and except in a few cases, we don't have a good constraint on that. And when we put these artist conceptions together, they're really artistic license more than anything else. So what we want to do in direct imaging to get around that is to study the planet, to actually see it. Of course, taking a picture doesn't mean that we'll map out these continents and oceans. That's not something you can do with any telescope we can build. But if you can see a planet and see the light from it, you can at least tell what it's made out of. You can feed that light into a spectrograph and measure its composition. And you can see different kinds of planets. The problem, of course, is it's incredibly hard. The analogy that I'm required by astronomer law to use is that it's like there was a lighthouse and you're looking right next to it to see a firefly, something that's 1 million or 1 billion times fainter. I actually saw somebody do this calculation once, and it's not completely crazy depending on the population of fireflies and the brightness of the lighthouse you use. But it's been done. The first time it was done is actually not for a planet, but for something called a brown dwarf. Brown dwarfs are objects that are really, we think of them more as failed stars. They're a cloud of gas that was going to form a star, but never got big enough, never got hot enough to have nuclear fusion happening to heat it up, and so they sort of sit there cooling down over time. But more than, not quite more than, a little bit less than 20 years ago, the first brown dwarf was discovered, sitting there glowing, sitting right next to a bright nearby star. And ever since then, because you can actually see brown dwarfs directly, we've studied them in enormous levels of detail. We wanted to, move beyond that to study planets. The phase 1 of this we did using the Keck telescopes. So the Keck telescopes are 2 10-meter telescopes in Hawaii you're probably familiar with. They're built in adjacent buildings, but 99% of the time you only use one Keck telescope at a time, mostly this one for me. Beautiful telescopes. Their primary mirror is the shape of a hexagon, super polished segments all attached together. They're on this mountain in Hawaii because that puts them way up above most of the turbulence in the Earth's atmosphere, but not all of it. And so even from the Keck telescope, one problem looking for a planet is that when you look at a star, turbulence in the Earth's atmosphere blows the star up into a big blob and you can't see the planet. Light coming from a star gets distorted by blobs of light in the Earth's atmosphere in all different directions. We fix that with a technology we called adaptive optics. We have mirrors that can change their shape, that can be bent by little electric actuators to take the rays of light from the star and bring them all back into a sharp focus. In a non-cartoon version, the adaptive optics instruments kind of look like this. The big telescope here gathers all the light, brings it down to a focus. The deformable mirror, the mirror that can change its shape, does that about 1,000 times a second to take all the rays of light distorted by the atmosphere and bring them back together. It does that in response to commands from something called a wavefront sensor that measures the turbulence in the Earth's atmosphere 1,000 times a second. Computer converts that into instructions for the deformable mirror and successfully makes the image better. We take a fraction of the light from the star and split it with a thing called a dichroic to that wavefront sensor. The rest of the light goes down to where we can actually do science with it. This kind of technology has been in routine operation astronomically on astronomical telescopes for about 15 years. And it can take something like this, which is an image of Neptune taken with a Keck telescope under good atmospheric turbulence conditions. You can kind of tell that there's something there. It's mostly round, although it looks surprisingly not round for a planet, and that there's some stuff going on it. You turn the adaptive optics system on and it looks like that. So it can sharpen up the images by factors of 10 or 20 to sort of Hubble's telescope quality images on our giant telescopes on the ground. With that, we can fix the light coming from the star, but we still can't easily see planets. Jupiter in our solar system is at about 1 billion, 10 to the 9 times fainter than the Sun. And that's too faint to overcome, even with adaptive optics, even with the Keck telescope. The second trick we use to find planets, in addition to the adaptive optics, is we look for the right kind of planets. And the right kind means young planets. So these processes I described for forming planets, in either case, initially, big cloud of gas, at the end, small planet. Big cloud of gas has a lot of gravitational potential energy because it's spread out over a large area. By the time you take all that mass and it ends up being a planet through whatever pathway it took, that energy gets released in the form of heat in the planet itself. So when planets form, they're hot. Jupiter now is sitting around at minus 200 degrees, but when Jupiter was brand new, it might have had a temperature of 3,000 degrees or more, glowing fairly brightly. By the time it's 10 million years old, 1,500 degrees, 100 million years old, 500 degrees, now minus 200. And that glow is detectable, especially if you choose to look at infrared light, which is the light that things give off when they have sort of warm temperatures. Planets become much, much brighter. So another graph. This is a plot of the brightness of the planet expressed as a luminosity relative to the Sun is what this means. So the fraction of the energy of the Sun that a given planet is giving off, from something as bright as the Sun, 1,000 times dimmer than the Sun, all the way down to 1 billion times dimmer than the Sun, versus age in billions of years, so 1 billion years sitting here. And each line corresponds to a different size planet, from 15 times the mass of Jupiter down to sort of Saturn size. And each planet starts out bright and then just gradually gets dimmer and dimmer and dimmer as they cool down. And if you catch them at 10 million year old ages, the planets are bright enough so they're only 10,000 times or 1 million times fainter than their star, which is still pretty faint, but a lot better than 1 billion that Jupiter is sitting at way down here right now. So by looking for planets that are young, which we can do by looking at stars that are young, the planets are potentially detectable. A complication in this is that this is another one of those sort of pre-Copernican graphs where people put it together assuming a simple process of planet formation. A more sophisticated approach to this accounts for the two different models of planet formation that I talked about. And in particular, if a planet forms through the core accretion process, form the core first, suck all the gas in, like we think our solar system formed, that releases a lot of the planet's energy early on, and later on the planet is dim. So one last version of this graph. This here color codes show each different size of planets, medium-sized Jupiter-sized planet, really big 10 Jupiter mass planet. If they form through the fast collapse process, then they're really, really, really bright when they're young and gradually cool down. If they form, on the other hand, through the core accretion process, like we think our solar system did, they actually never are very bright early on. They kind of sit there percolating away and then gradually rejoin the cooling tracks of the other planets. So it actually is a sort of mixed blessing. On the one side, it means where we're sensitive with our early equipment to sort of 10 to the minus 5, 10 million times fainter than the Sun. We can only see planets if they start out hot. But someday, if we could see both kinds of planets, maybe we could tell which way they form by looking at how bright they are versus time. So a bunch of groups searched using first-generation adaptive optics system for planets like this. This is one example of a success, probably the most spectacular example using that, the HRD 799 system that Christian Marois and a number of people, including myself, found in 2008 and 2010. So these are actual pictures of planets. What you're seeing here is the star kind of behind a mask. A lot of image processing has gone into it, but a little bit of leftover starlight, or these white blobs here and these black blobs here. But the dots are actual infrared radiation from 4 planets. The arrows are not giant arrows that were drawn on the sky. They're there to guide your eye in the process. The star is about 50% more massive than our Sun. The planets are about 5 to 7 times the mass of Jupiter. So they're big planets, about 1,000 degree temperature for the outermost ones, maybe 900 degrees Kelvin for the innermost ones. But they're real. So we can actually now look at a whole other solar system from outside and see its individual planets and see them moving around. In some ways, this whole other solar system is kind of like our solar system. We have 4 giant planets. It has 4 giant planets. Our solar system has a belt of asteroids and a belt of comets, the Kuiper belt. There's evidence from infrared observations this solar system also has a belt of asteroids and a belt of comets at large angles, and that there's a gap between those right where the planets are, which makes sense because the planets would clear out asteroids and comets there, just like they do in our solar system. Other ways, it's not like our solar system. The total mass of these planets is probably 30 times the total mass of planets in our solar system. Their orbits are bigger, but of course it's a bigger star, so it kind of makes sense that that's going on. And we can watch them orbit. This is just an animation Christian Marois put together of data going back to their discovery in 2008 to some 2013 or so epochs. The innermost planet is hard to see. You can only see it when the weather is really good, so it's not in all these blobs. But there's the other three. They're moving. They're moving like Kepler's laws say they should move. So this one is going really slowly because it's far from the star. This one is going quite fast because it's close to their star. It's not a surprise. Kepler's laws, of course, are Newton's laws. They apply everywhere in the universe. But the fact that we can see Kepler's laws from outside, that we can see a whole solar system going around the way once upon a time we would have just had animations like the one I showed you earlier, we can see in real data, real life, is actually pretty amazing. So I said why we might want to directly image these planets is to think about their composition, what they're made out of. We had our press release figure too, and I'll show one for 51 Eridani left, but of course we don't see that. We just see the dot of the planet. But because we can image it, we can actually say something more about its composition. So I'll just remind people a little about spectroscopy. Every element in the universe has a distinctive footprint of light that it gives off. The atoms that compose it have certain levels of energy they like to absorb or emit, and so it will only give off certain particular colors of light. And you've all seen this in your high school physics experiments or college physics experiments. If I have a cloud of hot gas and I feed the light from it through a prism, I'll get a particular distinctive chemical fingerprint. And that chemical fingerprint differs for different elements, helium, sodium, neon, etc. If you're a scientist, rather than looking at these color bars, you might choose to make a plot, a graph of the intensity of light versus wavelength. If you have a hot light source behind a cold cloud of gas, instead of seeing bright lines, you see dark lines where this cloud of gas likes to absorb certain particular wavelengths. And if I plot the intensity of light versus wavelength, you can see the dips as the intensity goes down, again, due to the chemical fingerprints. And so in turn, if I can get light from my planets, I can start to say something about the chemistry of their atmosphere. We thought their chemistry would look a little bit like this. So these are just stylized cartoons of the atmospheres of various objects. From right to left, the coldest stars have atmospheres that are mostly gas, but have actually clouds of materials that are solid at high temperatures, like titanium oxide. The brown dwarfs, especially the hotter brown dwarfs, those clouds live deeper inside the planet. Lighter weight clouds are higher up, and their atmosphere is full of carbon monoxide, which you could see in a spectrum. The cooler brown dwarfs, and we thought planets would look like cooler brown dwarfs, the clouds are even deeper in their interior. Up at the top where the atmosphere is cool, you can get compounds like methane. And so we thought we would see radiation coming up from the hot clouds through the methane, and we'd see the spectral fingerprints, the absorption lines of elements like methane when we looked at our planets. So we decided to look for this. Here's a Keck image without a lot of image processing now, showing what one of the planets looks like relative to the very bright star. And this is the field of view of the spectrograph we used for it. The spectrograph, the instrument called OSIRIS, is a very special spectrograph. It doesn't just measure the spectrum of one object at a time. Instead, it takes a three-dimensional picture where for every pixel in the image, I actually get a little microspectrum. I get the intensity as a function of wavelengths. So I can measure the spectrum of every object it looks at all at once over a small postage stamp field of view. And I can show that by animating this. Here's the total image with a little dot there that turns out to be the planet. All the streaks you're seeing in this image are scattered light, diffraction, and optical interference off the Keck telescope. Because they're a process made by diffraction, each of these little streaks, actually different wavelengths of light go to different positions in it. These are like tiny little extended spectra where red light scatters far away from the star and blue light scatters close. I can turn on an animation where I'm now stepping from long to short wavelengths, and all of the artifacts, all of the scattered light, have positions that change as you go from short wavelength out to long wavelengths, short wavelength out to long wavelength. The planet always stays at the same position at all wavelengths, and so you can use that to get rid of all the scattered light and say, yeah, there's the planet. Stack it up. And so we extract that, we do some math, we turn it into a quantitative plot of intensity versus wavelength, intensity, wavelength. And you can see in this is near infrared radiation because that's where the planet's bright, so long wave visible light would be somewhere off here, long wavelengths of light. You can see some chemical fingerprints. For example, carbon monoxide absorbs very strongly here. Water, this is absorption due to water vapor in the middle. We don't actually make a big deal about water vapor because it's hydrogen oxygen is the most common thing in the universe. Of course there's water. It'd be weird if there wasn't. But but there's a huge water vapor absorption signature present there. What there's not is methane is supposed to make a big absorption signature here, and it didn't show up. So we see the water. We don't see any methane. We see carbon monoxide. And the overall radiation we see, we think, is from hot, thick clouds of liquid metal. So it's confusing that we were seeing these thick clouds and not seeing the methane. What we think is happening is that the planet's atmosphere circulates, pulling up the clouds to the top of the atmosphere where we can see them, the clouds of liquid metal, and pushing down the methane where it gets destroyed in the inside of the planet. Because we can study its light, we can actually study it at very high levels of detail. Here's a zoom in on a different version of that spectrum. Here's the real data. And each individual little wiggle in this, especially out here, actually corresponds to a real feature from the spectrum, especially of water and carbon monoxide, but not of methane. We can use those models, I won't go through this in detail, but to measure those things like the ratios of carbon to oxygen in it. And we find that the planet is somewhat enhanced in heavy stuff, carbon and oxygen, compared to hydrogen in a way that says maybe it did form through the core accretion process like Jupiter did in our solar system. That was interesting. On the other hand, the planet is way too bright to have formed through that process. Back to this graph, brightness of planet versus age, the planets that form through the fast collapse process, the dotted lines, the planets that form the old-fashioned core way like our solar system, the solid lines, different colors meaning different masses of planets. The HRD 799 planets kind of live here. They're maybe 20, 30 million years old. They're only 10 to the minus 5 times the brightness of the star. And so it's really hard to make those through a core accretion process. They're too bright to form the way we think Jupiter did. But their chemistry says they form the way we think Jupiter did. So there's actually a lot of confusion about how you could form these planets. And in fact, although there are a lot of directly imaged planets, there's no clear consensus. Here's some other ones like Beta Pictoris, which is in the middle of a beautiful disk of dust, a couple of others with serial numbers. There's no clear consensus on how these directly imaged planets could have formed, and no evidence yet that they formed the way our solar system did. Showing this again, number of planets versus semi-major axes, all the Kepler discoveries, all the Doppler discoveries. If you're a direct imaging person and you show this graph a lot, it actually makes you a little bit sad, because of course there's 1,000 Kepler planets. There's only a handful of directly imaged planets. But some people's reaction is not to get sad, but to figure out how to do better. First, one thing that's interesting to do is show only the planets that we actually do have spectra of. It turns out for transiting planets like Kepler finds for a handful of cases, you can also measure their spectra. It's a separate talk that I'm sure you've had people do. I won't go into it. But every direct imaging planet, you can also do it. And so direct imaging is a large fraction of the planets that we've ever actually even gotten close to measuring their composition of. And so that makes us feel better. But really, we'd like to find, if not 1,000, like Kepler, which we're never going to do, enough more planets to fill in this direct imaging region, and also to bridge this gap. The farthest out we can see with Doppler techniques versus the closest we can see with direct imaging. Direct imaging, it's easy to see planets when they're far from the star. Doppler, it's easy to see them when they're close to the star. We haven't quite reached the point where those overlap, but it would be enormously powerful if it did. And finally, if we want to see more planets and maybe see the ones that formed in the cold way, we've really got to see fainter planets down to, say, this kind of ratio of brightness. And so that's the purpose of the Gemini Planet Imager. It's an instrument whose construction we started in 2004 on the Gemini South Telescope in Chile. It combines a whole bunch of different pieces I'll go through in a second. Physically, it's about the size of a person, or a robot in this case. This is the cube it mounts to on the back of the Gemini telescope. It's in a big enclosure. For example, you don't want a speck of dust on any of your mirrors, because that might look like a planet. So the whole thing is in the equivalent of a class 100 clean room when it's under operational conditions. Computers that control the adaptive optic system live in these enclosures off to the side. Another thing you don't want is the plume of waste heat coming from a fast computer going up through your telescope and making atmospheric turbulence. So we put the computers in these boxes. We circulate glycol liquid through the cabinets to cool them off. And then the main body of GPI lives in this interior box. It was built by a collaboration. Lawrence Livermore, where I used to work before I came to Stanford, built the adaptive optic system and also ran the whole project. A group at the American Museum of Natural History made some special masks to block the light from the star. I'll show those in a couple of slides. JPL built a very precise infrared sensor to measure small errors in the wavefronts of light coming into the instrument. UCLA built our science instrument, which is another spectrograph like OSIRIS that makes not just images, not just spectra, but 3D spectral cubes. A group in Canada, the National Research Council of Canada in Victoria, built the mechanical structure that holds the whole thing together, and equally importantly, the software layers that connect all these different pieces that have to talk to each other. There's about I would say about 15 person-years of software inside the instrument. We went to a lot of effort to super polish and keep all of our optics clean so they don't look like stars. One key technology for GPI to make it better than the current systems is its deformable mirror. So I showed the cartoon of a deformable mirror earlier. What a deformable mirror for atmospheric turbulence really is a thin sheet of glass, about 1 millimeter, so thin that you'd have to be very careful while you're holding it, maybe this big or so, with behind it a couple of hundred little actuators, little piezoelectric plungers that push and bend and warp the surface of it to respond to atmospheric turbulence. For GPI, we needed to do that not just at a couple of hundred locations, but at several thousand to properly keep up and correct for all the little distortions in atmospheric turbulence. If we'd built this with the same technology, little electric plungers glued behind it, the GPI deformable mirror would have to be kind of this big across, and it wouldn't have fit in that enclosure on the back of the telescope, and it would have cost on the order of let's say, $5 million or so. Instead, our deformable mirror is actually a microchip. It's a silicon device called a MEMS, a microelectromechanical systems device, which is basically laid down lithographically the same way microchips are, with 4,000 of these actuators in something kind of the size of a quarter. I mentioned masks to block the star. We kind of smooth the transmission of the telescope so it doesn't have sharp edges to diffract off of, but kind of looks like this donut mask. And then we focus the starlight down onto a mirror with a hole in it such that the star falls down, the planet comes to a focus off to the side, and we separate the two so we can measure the spectrum of the planet that way. We built the whole thing at a bunch of different places, then integrated it not far from here at UC Santa Cruz. We installed the infrared spectrograph in 2012. The instrument has to operate in a fairly tough environment on the telescope in Chile. You're on the back of a telescope, so as the telescope points in different directions, the instrument might bend, and it has to stay aligned to within about 10 microns or so that's not acceptable. So we put it on a crane, we cranked it all over the sky, we saw how aligned it stayed. When it moved, which of course it does, we measured those motions and we programmed the computers to compensate for them by steering mirrors in opposite directions. Similarly, it has to work not just at kind of room temperature, but down to -3 or -5 Celsius, which is the coldest it's supposed to get at Chile. So we built a giant meat locker around it and then chilled the whole thing down to -5 Celsius to make sure all the computers worked and that it would stay aligned over a broad range of temperatures. And we did that successfully. We packed it up and shipped it. It's a sort of disconcerting experience to see 10 years of your life packed into crates. My small child helped with the process of packing and shipping. Put it on a truck. You can't drive to Chile. Turns out there's no roads all the way down there. So the truck took it to Los Angeles, and then a LAN Airlines 767 took it down to stopping briefly at Lima, and then continuing to Santiago. And then another truck took it from Santiago to La Serena. I did not watch this process because, first of all, I don't speak Spanish. I wouldn't have been that helpful. And secondly, again, 10 years of your life on a truck going up twisty mountain roads so I was just sort of heavily drugged at home until it actually was delivered. We could follow it, and it made it there intact. So it was unloaded by Gemini. There's the telescope. There's the Chilean truck. Sat in their basement for a couple of weeks. I did fly down to be reunited with it. Glad that it survived the trip. Bolted it onto the back of the telescope. A nice thing about the Gemini telescope is here it is now on the back of the telescope, like in the diagram we saw before, looking up, so light from the telescope comes down into it. You can actually attach multiple cameras and spectrographs to the Gemini telescope. These are some of their other cameras and spectrographs, and so that's nice because while we were getting ours tuned up, they could do science with their other instruments. Our first flight, almost 2 years ago now, large team of scientists and engineers from a bunch of institutions down there for it. Data coming out from GPI, you'll see a bunch of examples of this. Just like with the OSIRIS instrument, it's not an image, it's a spectrum of every pixel. So here's another animation from long to short wavelengths of infrared light. This is just of Neptune in our solar system. As you go through the spectrum at every pixel, we get the intensity of light as a function of wavelength. And in Neptune, you can actually see some of this atmosphere structure. For example, these clouds here are way up near the top of Neptune's atmosphere, and so they stay bright. A cloud that's deep inside Neptune's atmosphere gets much dimmer at the wavelengths of light where methane absorbs because Neptune's atmosphere is full of methane. For early GPI science, we concentrated on planets that were already known to exist. This is the planet around a star called Beta Pictoris, Beta Pic B. What you're seeing here in this GPI image, here's the mirror with a hole in it. The star fell down that hole. This is kind of a glint off the edge of the hole, leftover light and diffraction coming from the star. The 4 spots you're seeing here are not planets. They're spots that we induce in the image as a calibration. And the reason we induce them is that when you find a planet, one thing you'll want to know is how far is it from the star. If the star disappeared because it fell down the hole, that's hard to measure. These 4 spots are actually lined up so that the intersection of them is always where the star is, so you can trace the star position very accurately. The planet is that little dot here. So that's another big one, about 10 times the mass of Jupiter. For comparison, here's an image from a previous generation instrument, the people who discovered that, not the people who discovered that planet, another group. After it was discovered, planet's visible, planet's more visible in the GPI image, so we're somewhat happy. But we're extremely happy because this took 3,952 seconds of telescope time, and that took us 60 seconds of telescope time to make the same image. So GPI is, in fact, substantially more sensitive than its predecessors. And so we were happy. GPI has looked at a wide variety of objects. I think James talked about some of them in his talk. I don't have time to discuss it in detail, including disks of asteroid or comet material orbiting stars, Europa and Pallas, some images that Franck looked at, young disks that might be in the process of forming planets, a whole bunch of other planets people have known. But what I'm here to finish up about is talking about our first new planet. So here's another one of those spectral cubes. I should get a version without the arrow to see if people can spot the planet, because what happened literally was we started looking for new planets in November of last year. So we're targeting a population of young stars, about 600 of them, to see which have nearby planets. We had an observing trip in December right before Christmas. All of us went home pretty much, except for one grad student and one postdoc at Berkeley. And the postdoc, literally looking over the grad student's shoulder at a computer in Berkeley, saw a little dot that was kind of coming and going. All these artifacts sort of hold still, but this little dot is coming and going because the brightness of the planet is changing as a function of wavelength. And here's its spectrum. And it's changing exactly the way our model said cold planets should, where light is being absorbed by methane and emitted by the hot clouds deep in the interior of the planet. The star is about 20 million years old. If it's really a planet, it would be orbiting around where Saturn does. And so the first question we asked ourselves is it really a planet? It turns out there's a large history of thinking you found a planet and being wrong in this game for a lot of reasons. One of the most popular reasons is what we see here. Here's the images from GPI again and a Keck image. We actually took an image with the Keck telescope, so at least we know it's not an artifact from the telescope because it's there with Keck as well. You see something very faint next to something very bright like a star. One explanation is you're seeing something very faint because it really is very faint. It's a planet right next to the star, and planets are faint. Another explanation is it's very faint not because it's really faint, but because it's very far away. It's another star that, through an astonishing coincidence, happens to have lined up right next to your star. And it's not that astonishing coincidence if you do this for years and years and years and years. And in fact, I believe my ratio of actual discovered planets to background objects is about 5 to 400 or so over the course of the career. So traditionally what you do is you come back a year later and you look for motion. If it's really a planet, it'll move with the star, plus maybe orbiting around the star. If it's really a background object, it'll either hold still or wander off in some separate direction. We didn't want to do that, partially because we've been doing this for a long time and we're not very patient, but also partially because we didn't think we needed to. We did observe its position at multiple eras. This is a graph Eric Nielsen here at SETI put together. Here's the year versus the position of the planet. When I plot these, I plot the separation between the planet and the star. That's the top one. And also the angle that the planet and the star make. That's the bottom one. We saw the planet in December of 2015. We confirmed it after Christmas in December 2014, January 2015. But that's such a short period of time. The gray track is the path a background object would have followed. The cone is the range of orbits a real planet could have followed. And you can see over this short period of time, there's no way to tell the two of those apart. We did dig through a lot of archives, and we discovered half a dozen other groups had looked at this one individual star to try and find planets. None of them had seen it, of course. They would have published it. We took, for example, some old Keck data from 2003. We analyzed it very heavily to see if we could see the planet, which would have been about here. We couldn't see the planet. It makes sense. Keck is less sensitive than us. But that does actually help us tell if it was a background object. The star is moving kind of this way. And so if it had been a background object, the star would have left it behind. It would have been farther away from, the star is moving towards the planet. So if it had been a background object back in 2003, the star would have been further away and would have been just barely detectable by Keck. And in fact, we can sort of exclude a range of allowed motions for it. This is a plot, again, Eric put together of now the separation between the planet and the star. We know way back in 2003, the planet had to be within this range, not right on top of the star. We know where it is now. And so we can partially constrain the fact that it's not at least a stationary background object. So that helps. But it could be a background object that's still moving. And in fact, the referee on our paper said, you should reobserve this free. It was just very snarky about, this is the gold standard. And if people publish a paper that doesn't go up to the gold standard in science, they may be right, they may be wrong, but it'll be a bad example for the kids, and everybody else will be publishing planets that aren't really planets. We did not find that compelling as an argument. What we did find compelling is that because it's GPI, we have a spectrum. And stars don't look like planets. Here's the spectrum at short and longer infrared wavelengths. And it's got this enormous signature of absorption due to methane. Stars don't have methane in their atmosphere. What does have methane in its atmosphere are either real planets or things called brown dwarfs, objects that are in between planets and stars. And the thing about the brown dwarfs is they're incredibly rare. The odds that you would get to find a brown dwarf, you have to survey pretty much the whole sky and you find 100 of them. The odds that you'd find one right next to your individual star, nearly zero. And in fact, the most compelling, not the most compelling quantitative argument, we did the calculations and we say that there'd be about 1 or 2 per million stars we look at, background objects that we would actually find. So the odds of it being a background object are relatively small. An example of that is that as I said, a whole bunch of other people looked at this star to see if it had a planet or not. They looked at it with cameras with huge fields of view that are just as likely as we are to find background objects. In fact, more likely. The only place we can look that they can't is right next to the star. Background objects should be anywhere, planets right on top of the star. So the fact that we found it with a planet imager, it even says that on the label, means it must be a planet. I won't go through, as I'm running low on time, in detail, but we know the age of the star very precisely because it's actually part of a triple system. Here's another figure Eric put together. The star and its little planet are over here, and then there's another pair of stars that are orbiting around them in this complicated ballet. This pair of stars, they're relatively low-mass stars, and you can measure their age very precisely. We did put together a very cool animation. Jennifer Patience, faculty member at Arizona State University, together with her planetarium, and Danielle and Franck working through here, put together an animation showing the system. Like HRD 799, this system has a comet belt, comet equivalent belt, and an asteroid equivalent belt. And the planet is kind of in between them, which is probably where planets should be. As we zoom in close, you can see the planet sort of sitting there, Jupiter-like, but glowing, because what we see is the infrared glow from it. And in this figure, as it zooms around, you can also see the other 2 stars in the system. I don't actually know. Franck might know if they got the orientation of the Milky Way right or if this is just arbitrary. But it doesn't really matter. Missed the double system. All right, I should have pointed it out. I said you should be distrustful of all these gratuitous artist conceptions, which is sort of true. But we don't have an image that looks like that. We do have this spectrum. And from this spectrum, you can take models that tell you things like what the surface is like, what the atmosphere is like, excuse me. And in order to reproduce the bumps and wiggles in this spectrum successfully, we have to have an atmosphere that is kind of half covered by clouds that are cold at the top of the atmosphere, but half without clouds, where you see deep into the hot interior of the planet. And this artist conception that Danielle and Franck put together actually reflects that. So I don't know in detail that there's 5 bands or 7 bands. I don't know that the bands are elongated or there's a giant red spot. But I do know that if you were to look at this planet with your eyes, you would see a surface that's sort of half glowing deep on the inside and half dark and opaque clouds on the top of the atmosphere. And then finally, in terms of its formation, this is sort of the first planet that could have formed either way. Here's another version of those formation graphs, brightness of planet versus time. All the previously discovered planets are way up bright, where hot start planets could have formed. This one is sitting a little bit under 1 million times fainter than the sun, where potentially a planet that formed like Jupiter would be sitting at this age on this particular graph. We can't tell for sure. It could be a very small planet that formed hot and just isn't bright because it didn't have a lot of energy to start with. It could be a big planet that formed cold and is not very bright because it lost a lot of its energy forming as its core, as it accreted mass on its core. But someday we may be able to tell the difference. If we could ever measure the mass of the planet, and there's some hope that in 5 years we might be able to do that accurately, we could tell whether it sits on this hot start or cold start family of curves. So to summarize, it's about 20 million years old. We've seen it since, it should say December 2014, excuse me. Temperature about 650 Kelvin, 2 times 10 to the minus 6, the brightness of the sun. The odds of it being a background object are less than 10 to the minus 5. The mass might be twice the mass of Jupiter at a separation of Saturn. Not quite our solar system, but getting there, and young enough that it remembers how it formed. And then just as a hot off the presses, I was in Chile, what day is it? I was in Chile a week ago. And we saw that the planet is still there, which is kind of reassuring. Before we went there, Eric and his summer student Sarah did some modeling of the range of motions it should have. It's actually pretty close to where the range of motion, where the predictions say its motion should be. And over the next 6 months, we'll be studying it in a lot more detail. And so I think I'll finish there rather than going into the space mission stuff, but I'm happy to talk about future space missions with other people. So.
Hi Bruce, nice talk. So my question is, what are the chances that GPI would be able to image a planet by reflected light rather than self-luminous light?
Say Alpha Centauri or something like that, not to put too fine a point on it. It's, right, Russ kind of knows the answer to this, but it's a good question to ask. And GPI wasn't designed to do this. It was designed to look for the self-luminous planets. The signal from a reflected light planet is very small, but not completely out of the question, and especially if you took advantage of polarization. So one capability GPI has that I didn't talk about at all is it can measure the polarization of light as well as its spectrum. Light that's scattered by turbulence in the Earth's atmosphere is unpolarized, or light that's scattered by the dust on the telescope is mostly unpolarized. Light that reflects off a planet might be polarized, and if it is, that would help us pick that signal out. So if planets have significant polarization fractions like 10 or 20%, then a 1 or 2 AU planet around maybe even 4 or 5 stars would be within the detectable range if you persuaded the observatory to let you spend 10 or 20 or 30 hours on it. So I'll do Epsilon Eridani, you can do Alpha Centauri. It'd be a good combination. There are models that predict the reflected light polarization. The Europeans are maybe looking for it, maybe not. The self-luminous planets we talk about might also be polarized, but for reasons too complicated to go into right now. But GPI is shown to be very, very good at making those precise polarization measurements at the part in 1,000 level. So our speckle suppression factor for polarized light might be 10 to the third, which does get us down if we have enough photons into the regime where we could hope to see these things.
Can you tell us more about debris in 51 Eridani? Is it imaged or is it just from the spectral distribution?
It's just from the spectral energy distribution. So we can tell these debris disks most often because the dust from the asteroids and comets colliding with each other absorbs visible light and radiates infrared light. So the signature is you see extra infrared light from a lot of stars, and you infer that that's from dust material or aliens, but dust is probably a more robust experience in general, though people talk about Dyson spheres and things like that. The 51 Eri case, its dust disk is actually pretty thin for such a young star. It's probably only about 10 times as much as the amount of dust in our solar system, which for a 20 or 30 million year old star is quite young. So it's almost certainly undetectable, especially because the planet notionally clears a gap in it. Somebody I'm sure will be looking for it with the Hubble Space Telescope, which is very good at seeing dust at relatively wide orbits, but there's no detection yet.
So I know with brown dwarfs you can see patchy clouds or some kind of cloud modulation as the planet rotates. Has the spectrum changed when you went back to look at it again, or do you think it might?
Just got off the airplane a week ago, so
okay.
So ask me in a little bit. People certainly do think it might for some classes of planets, that you'd see the same kind of modulation as the clouds come in and out of field of view. It's a hard measurement. You could see how big the error bars are on that spectrum, but it's certainly on our list is to try and monitor it. And the trip I was in Chile for 5 nights, and we only really had one good night, so can't tell yet, but I think it's unambiguously worth pursuing, especially if it is at sort of 45-degree or more inclination.
Bruce, great talk. Did you mention that you've got future work queued up in slides that you could show us in a minute?
I had a little bit about future space missions, especially the W1st AFTA space mission.
I wouldn't mind seeing a slide or two if we've got time.
Well, we've got a couple minutes. I mean, we're a little past the hour, but if nobody's flying up.
People can leave, too. You know. Yeah. I assume they unlock the doors at this point.
W first. Yeah, W first.
Let me just do 2 or 3 slides on. I also had a little bit about the 30-meter telescope. So the broad question beyond is GPI is really limited still to these Jupiter-size or bigger than Jupiter-sized planets. Kepler says that's not the most common kind of the planet in the universe. How are we going to characterize them? A lot of missions will do it, including the TESS mission, the sort of son of Kepler, but ground-based imaging has a role to play too. The first way to do it is to put something like GPI on a really big telescope, like the proposed 30-meter telescope in Hawaii or its equivalents in Chile. That would probably get down to kind of Neptune-y planets and scrape the super-Earth regime. Another approach would be future space telescopes. Russ is involved in a proposal for one that would reach exquisite levels of sensitivity around very bright stars, so to probe Alpha Centauri. A broader version for slightly bigger planets is something called WFIRST. So the acronym, it's going to get a real name when we fly it, but for now it's WFIRST, Wide Field Infrared Survey Telescope. So the first part of its name tells you what it was originally intended to do, which is to survey the whole sky at infrared wavelengths for dark energy, cosmology, stuff that a number of my colleagues find extremely, I'm being videotaped, aren't I? Stuff that a number of my colleagues find extremely exciting. And so it was proposed and ratified by the sort of astronomical community as the most important thing we could do in the next decade. It was originally going to be so the second part of the name, astrophysically focused telescope assets. That's even worse than wide field IR survey telescope because it's not a word. Where does that come from? So WFIRST was originally going to be about a 1.2 meter, sort of Kepler-sized telescope, extremely wide field of view infrared camera, and it would basically do counting galaxies and measuring their shapes. And over a 3 to 5 year mission, it could only do that. Then something weird happened. So the way I explain this is, let's say you like hiking a lot. You might buy hiking boots, and they might be on sale. So you might buy a bunch of hiking boots. And then you might forget you have them. And you open your closet, and you discover you've got 8 pairs of hiking boots. Clearly too many. You have some friends, so you say, would you like some of my hiking boots? You donate them to them. The same thing happened with the Department of Defense and NASA, except instead of hiking boots, you should think Hubble Space Telescope-sized telescopes. So the Department of Defense opened their closet, and they discovered, I do not know how many they have, but they definitely had too many Hubble Space Telescope-sized telescope assemblies hanging on a hook somewhere. And they donated 2 of these to NASA. So 2.4 meter telescope assemblies, not whole spacecraft, just the telescope and the optics, but designed for wide field of view, so great for the dark energy science, big, optically good, robust, and available. And if you're going to do that, I'll skip this animation, although it's very cool. There are a couple of good things. 2.4 meters, first of all, it's big enough that it can do the extremely exciting galaxy counting stuff much faster, so it doesn't take all 5 years of the 5-year mission, which gives you some time to do other stuff, like, say, look at planets. And it's big enough that you could actually use it to do direct imaging of exoplanets, which is hard to do on a 1-meter telescope, but very practical on a 2.4 meter telescope. So the baseline is to add something basically that looks like GPI, a deformable mirror, a coronagraph mask to block starlight, an integral field spectrograph, and fly it on this and do characterization of extrasolar planets in reflected light. And in the usual mass semi-major axis diagram space from some simulations Dmitry Savransky at Cornell did, it could reach down to maybe even Earth mass planets, but definitely to the sort of super-Earth planets, several times the mass of the Earth, and expect to discover, get photometry, maybe spectra, maybe not, but definitely characterization of a decent sample of those if it flies, which it has a good chance of doing in 2024 or so. Okay, so that's the WFIRST sideline.
Well, if there's no other questions, I would like to, you want one last quick one?
Excellent question. So if you were to, no atmospheric turbulence, but there's still imperfections in the mirror of the telescope. It's better than the Hubble mirror. It doesn't have the big spherical aberration in it. But just the act of polishing it puts tiny little ripples in the mirror from the tools you use to polish it. To actually see a planet without any correction, the size of those tiny little ripples would have to be smaller than an atom. They would have to be a tiny fraction of an angstrom or a nanometer. You can't make a mirror that precise, and you can't count on it staying that precise as you fly it in space. So the deformable mirror cancels the aberrations intrinsic to the optics, as well as more complicated diffraction. Russ is wincing because I'm oversimplifying this, but as well as more complicated optical effects intrinsic to the design of the telescope. So it's to fix the little polishing errors and imperfections. That's why you can't do this with Hubble, but you couldn't do this with any space telescope. It's much easier to build it properly, much easier to correct it rather than to try and polish it at that sub-ultra mega nanometer level.
Okay, one last question.
I was wondering, with GPI or maybe future surveys like this, is it at all possible or likely that we could get a long enough time interval of observation of a single planet that we could look at variations in its orbit and actually infer whether there might be lower mass, less bright planets in that solar system caused by those, causing those variations?
That's a good question, because Kepler does things like that, of course, in timing of eclipses. It's unlikely. So the fastest orbiting planet that groups I've been involved in have been discovering is sort of a 30 or 40 year period. And so right now I'm trying to exercise better and eat well so that I can see it do a whole orbit. But to see these perturbations, you really need multiple orbits and very precise levels of astrometry. But who knows? We may get that precise going on into the future.
All right, well, with that, I would like to thank our speaker, thank Bruce for wonderful talk. And this is the part where our speakers treasure most. This is where we hand out the revered SETI Talks speaker's mug. These are highly valued and prized. I think on eBay now they're about 50,000 a piece. So anyway, very rare, but thank you so much. Great talk. All right.